Okay, excellent. So today we are going to talk about the hypothesis learning and extension of the Gaussian methods beyond the toy one-dimensional systems that we used in the first two lectures. So first of all, let's do a little bit of the recap because generally it is a good idea to keep track of what are the absolutely essential components of the active experiment and what are kind of additional. So in the first lecture, we went through the concept of the Gaussian process through the, so what it is, what is kernel function, what are the kernel priors, what are the noise priors, what are the posteriors, and we introduced the concept of the Bayesian optimization based on the Gaussian processing. So the key element there was the acquisition function. So this is something that is absolutely important to understand and plan automated experiments. So in the case of Bayesian optimization or myopic workflows, we have the acquisition function. If we have the multi-step workflows, such as be operated by reinforcement learning, then we had the reward functions. And the equivalent of the acquisition function in reinforcement learning would be a policy, meaning how do you, what are the rules by which you perform actions depending on where you are. So in the second lecture, we went through the concept of the Bayesian inference, which is some sense a physicist approach to the probabilistic problems. We went through the concept of prior and posterior distributions, and we compared the Bayesian inference with the least square fit and introduced the WAEC as the way to choose the right model. So we also looked at the structured Gaussian processes, where we choose the probabilistic physical model and use it as the mean function in the Gaussian process. So with this, we actually started to go into the unknown a little bit because whereas the Gaussian processing is a more or less standard field now, so it is used across the board for the last several years, both in synthesis, in instrument optimization. Obviously, it's used a lot in the machine learning community for the hyperparameter selection, so on. Structured Gaussian processing is a different story. So this is there is a relatively small amount of literature about them because it is heavily domain specific. So given that in most scientific domains, this type of approaches are uncommon, there is not that much you can use. And we also introduced the concept of the prior distributions and posterior distributions. So basically in structured Gaussian processes, it is a hybrid of the normal Gaussian processes and the Bayesian inference. And we also looked at the example of the structured GP-based Bayesian optimization and looked at the ways how it can go right and how it can go wrong. So the short answer is that if you know the physics more or less correct, structured Gaussian optimization works much better than a simple Gaussian process. If your physical model is incorrect, but you are very certain on it, you can easily get trapped in the wrong minimum. So just as the reminder, structured GP is the extension of GP where our mean function is not zero. And this obviously gives rise to quite a lot of mathematics. So the rules of how you update the Gaussian process at each step become a little bit more complicated. The good thing is that once you use the GPax, all of this complexity is hidden under the hood. So all you need to care about is how you specify the probabilistic functions and its priors. And this is how it roughly looks like. So if we use the simple Gaussian processes with the zero mean function, then our Gaussian process is basically the multivariate Gaussian distribution around the zero mean. So if we do the experiment, meaning we fix the value of the function at several values, then out of all possible functions, we choose the ones that actually pass through the points where we took the measurement. So it's not a very rigorous parallel, but you can compare it with the wave function collapse when you do the quantum measurement. So before you do the measurements, everything is possible. After you do the measurements of all the possible prior functions, the only one that survived are those which are consistent with the experiment. And then once we have all the possible posterior functions, we can average them to give the posterior mean function and the uncertainty. And these are the ones that we use in order to select our policy for the active learning. So in structured Gaussian process situation is different. In this case, our prior predictive distributions are sampled from the probabilistic model. And the probabilistic model is where the physics is actually come into play. So we can choose the form where you have the function with the two maxima, the maxima shape is Lorentzian, and you can ascribe the certain value, certain prior distribution to the parameters. So this is exceptionally powerful approach. And I've shown you the example of how it works for compared to the normal Gaussian processes. So where's the jumping? So in the normal Gaussian processes, we have trouble even describing the function with the single discontinuity. So this simply follows from the fact that the kernel has to be, kernel length can be large here, but it can be very short here. If the kernel length is short, then the Gaussian process will repeat the measurements in these regions in order to make sure that there are no other jumps in these regions. Comparatively, if we provide the structured model where we have a single jump, in this case, we identify the position of the jump relatively fast, and then essentially our automated exploration is finished. And of course, it works for the two-dimensional cases. So this is something that we discussed last time in length. But then you can ask a question, what are we going to do if we have more than one potential mean function? So when we run the physical or chemical experiments, we typically talk about having the hypothesis. So obviously, all of us intuitively know what the hypothesis mean. I will not be surprised that all of us have a roughly slightly different definition of how it goes, what exactly it is. But roughly you can identify the hypothesis with having some model of the process that can go on. So the purpose of the experiment is always to either falsify the hypothesis to find out whether it is true or not, and to refine the model parameters numerically. So the whole history of where the hypothesis come from and what is philosophically meaning goes back to 30s, to times of people like Popper, Wittgenstein, and so on and so forth. It can be very interesting reading. And interestingly enough, if you want to apply machine learning in active experiment, this type of concepts stop being philosophy and become very much a part of your research. But for the time being, let's just go to the case where the hypotheses are embodied in the form of models. So then what we want to do is to run some sort of experiment, whether we do synthesis, film growth, any kind of reaction. And let's assume that we do measurements one by one. So we explore the compositional space, we can explore the parameter space, sort of choose your favorite experimental setting. So the result of this measurement, of this experiment, is a physical measurement. And for simplicity, we can assume that the measurement just gives us a single scalar answer. So what we can do is to send this answer to our structured Gaussian process model, which is also informed by the list of possible hypotheses, meaning that the models that can describe the system behavior. So the purpose of our active experiment is twofold. One is, given the list of hypotheses and experimental result, we want to go from the priors to posteriors. So we want to update our model parameters. So this is the part that we actually do with we can also do with the Bayesian inference. We can use the hierarchical model. But then we also want to ask ourselves a question: can we use the list of hypotheses and the physical measurement in such a way as to choose the next most informative measurement in our parameter space. So as a simple example, if we have a compositional phase diagram, so if we synthesize the hybrid perovskite, let's say we have synthesized 3 compositions, what should be the 4th composition which you want to choose to synthesize? If we explore the optimization of some organic reaction, if we perform the process in several positions in the parameter space, for example, using several ligands or solvents, how we are going to choose the 4th, 5th, and so on location. So this is not very different from the way that human operates, except that humans do it based on the combination of intuition, common sense, and some amount of luck. The question is, can we train machine learning to do something like this? And it turns out that it is possible. There are several ways of doing it. So the complex way is to essentially create the high-dimensional probabilistic Gaussian model when we have models with their probabilities. It may work. The only problem is that it is computationally very intensive. So there is a simpler way of doing it, which is where we choose models to compete with each other. So effectively, we can combine the ideas from Bayesian optimization and ideas from the reinforcement learning. So if we run the experiment and we have several hypotheses, we choose our next experiment in such a way as to minimize the uncertainty of our hypothesis in the fastest way possible. So we want to maximize our knowledge, and in order to maximize the knowledge, we of course minimize the uncertainty. So I'll show you the example of how it is incorporated in the code, but before we go there, let me show you a few examples of how it actually operates for model systems. So imagine that we have several models, sort of model 1, model 2, model 3. We run some automated experiment, and we start with the model 1. So in this case, the experiment runs for a few iterations, our uncertainty minimizes, but then we explore the component which is called the epsilon greedy search, meaning that even if our models start to fit the experiment, let's try another model to see how it works. And in this case, we try the model number 2, and you see that this model does the prediction with very high uncertainty. So prediction with a very high uncertainty means that this model probably doesn't match the experimental results particularly well. So our algorithm reverses back to model 1. Then it kind of goes between model 1 and model 2, and then it tries the model number 3. So in model number 3 gives us much low uncertainty. So why does it work? Remember our examples of the Gaussian processes. If we try to force the Gaussian process to describe our data, but the functional form of our mean function is incorrect, it kind of tries to do it through the GP part. And then you see the large predictive uncertainty. But if somehow we have the right functional form, then our predictive uncertainty is very low. So if we, it's almost like being a scientist in the lab 30, 40 years ago. If the experiment fits the model very well, we intuitively feel that this is the right model. And then we don't have to have a large amount of experimental data to actually convince ourselves that this model is correct. So this is exactly the same principle. If the model is correct, then it gives us low predictive uncertainty. And the active learning basically tries to explore this model space. And once it figures out that the model number 3 gives us the lowest uncertainty, we make a conclusion that this model is actually a correct one. We still check the other models just to make sure that we didn't find evidence to the opposite somewhere. But still, that's how it works. So how can we use it for the real world applications? So the first example that we worked on was the combinatorial library of the bismuth ferrite doped by the samarium. So this is a very cool system because on the one end, it is rhombohedral ferroelectric material. On the other end, this is the paraelectric orthorhombic material. So basically moving across this phase diagram gives us the cross-section of the phase diagram. And we know that in the center, there should be some interesting and unusual phases corresponding to the morphotropic phase boundary. So, and in some sense, this was the whole motivation of starting this research several years ago, because we know that if we choose the right location, we can understand the physics of this material. Problem is that the electron microscopy measurements are expensive, and so are scanning probe microscopy measurements. We cannot do the measurements every 3 microns, because that will give us 300 measurements overall. So that's way too expensive. So question becomes, can we use the active learning in order to navigate this phase diagram in a more intellectual way than just across the grid? So the first question is, do we have a signal? So if we take the sample and put it under the microscope, would our measured signals change? Actually, it would. So on the one end, we have the topography and the piezo response images looking like this. So you can see beautiful stripy domains and relatively flat surface. So in the middle, our domain pattern is totally different. Topography is still roughly the same. On the other end, where we don't expect any ferroelectricity, we kind of don't see much in the PFM signal. There are some splotches, and topography again is kind of comparable. If we try to measure the hysteresis loop measurements across the several locations, we can see that the hysteresis loop shape changes somehow across the sample. Great. Can we use the hypothesis learning here? So the key element in the hypothesis learning is to create the models of the system behavior. If we the model can be in the form of the symbolic expression, that of course is the most convenient. The model can be numerical model. If the model is numerical or computational in nature, we have two alternatives. One alternative, that this model can be evaluated fast. Then we can use the hypothesis learning. If the model is expensive, so if we want to use something like quantum Monte Carlo, and the model is as expensive as the experiment, then we don't use the hypothesis learning. Then we need to go in the field which we call the co-navigation between the experiment and theory. So this is something that we just start to scratch the surface. So we are not going to go there for the purpose of this workshop. But if the model is relatively cheap and more or less consistent with the experiment, meaning that it's sort of, we can compare apples to apples, we can use the hypothesis learning. If we have one model, we will just use the structured Gaussian process or even Bayesian inference. If we have 2 or more models and we are not sure which one is correct, that's exactly the case where the hypothesis learning is applied. So this is the first example where of the experimental measurements. So this was actually done manually. So at that time there was no automation for the stage there. And Yongtao ran 12 iterations of manual experiment. And as you can see in the end, it looks like the model 1 and model number 2 give us roughly the same answers. So that's unsurprising, because model number 1 is the second order phase transition, so it sort of predicts the smooth decay of the signal. Model number 2 is the first order phase transition, so you see the sample predictions for both of them rather clearly. The problem is that our signal actually increases as the function of the concentration, and for both models, it predicts that it should smoothly go down. So in this case, we tried. Our experimental result is simply not consistent with either of our models, and therefore the experiment is inconclusive. So good thing to know that it's not always work. This is the second example where it actually did work. So in this case, we studied the phenomenon of the polarization switching by the AFM tip. So this is something that the whole piezo response force microscopy community explored for maybe 30 years by now. And generally the setting of the experiment, and that we have the bias probe, we put it on the surface, we apply the bias, that causes the material to switch from polarization down to polarization up. So the question becomes, what limits the size of the domain? So it turns out that we can enumerate the exclusive list of the possible scenarios. So in one model, our size of the domain is determined purely by the thermodynamic of switching. So in this case, the domain size depends on bias that we apply and doesn't depend on time, because thermodynamics is obviously time independent. Our second model is also thermodynamic, but it is derived using different approximation for the depolarization field. So, and we can show that it's either this case or this case. We can have other physical mechanisms that limit the size of the domain. For example, if we apply bias, then the size of the domain can be limited by the pinning of the domain wall on the disorder inside the material. So in this case, after kind of playing with the math a little bit, we can come up with the model that predicts that the size of the domain as the function of the tip bias and time of the pulse would be the power law function of the bias and the logarithmic function of the time. And finally, we have a third limit case when if we apply the bias, the switching of the domain is controlled by the injection of the charge carriers on the surface. So this is just a depolarization field effect. So in this case, we expect that the switching would be a power law in voltage and power law in time. So between the thermodynamic limit, wall pinning limit, and charge injection, this seems to be the full list of possible scenarios. So it has to be one of those. More importantly, looking back at the history of the field, I know that there are examples of this type of behavior, there are examples of this type of behavior, and there are examples of this type of behavior. So it looks like a good list of hypotheses. And then this is how we set up our active learning experiment. And this is the schematic of where the active learning is actually implemented on the operational scanning probe microscope. So you have, this is an example of the intermediate system. So in this case, the most of the work was actually connecting things together and convincing them to work to talk to each other. So this is a real accomplishment. Going forward, I really hope that the experimental system have the Python APIs, because that will minimize the level of effort by about 80%. So you can focus on science rather than engineering. But the first time it is done, it is necessary to make the connection. This is how it, oops, why is it not working? Apologize. Somehow this animation stopped working for reasons that I don't quite understand. But anyway, what you would have seen is how the machine learning agent passes the commands to the microscope. So it will issue the command to scan the region of the surface to determine the domain size, apply the bias pulse to the tip in order to switch polarization up and down, and then it will issue the command to image the form domain. And while the domain is imaged, it will figure out what should be the next parameters of the domain wall. It doesn't work. Sometimes the PowerPoint says that there is an issue with the codec, but anyway, I'm not going to solve it now. But this is how the recording of the experimental protocol looks like. So this is the data that is generated from the microscope. So this is the ferroelectric domain that forms. This is our parameter space, the bias applied to the tip, and the length of the voltage pulse. This is how the microscope processes the data, so it automatically determines the domain size. And the workflow is fairly straightforward. So we start with measuring the behavior of the system and several initial seed points. Then we train our hypothesis learning algorithm, and then we start to figure out which of the hypotheses is correct. And you can see that in the beginning, it looks like the system prefers hypothesis number 3. Then it tried all possible hypotheses from 1 to 4. And then by the end of the experiment, it clearly establishes the preference to the hypothesis number 3. So this is actually pretty interesting, because in this case, we actually realized the microscope as the automated scientist. So we had 4 competing hypotheses. They represent the full set of possibilities in the system. The microscope chooses the experiment to run in such a way as to establish which of the hypotheses is correct fastest. And that's kind of great because this is the case where the machine learning actually becomes a part of the hypothesis-driven discovery. So the important thing is that the same approach can be implemented in synthesis or pretty much any other measurement as long as the list of hypotheses is available. So for the time being, our colleagues at UT Knoxville have implemented the hypothesis-driven discovery for the engineering the bandgap, the hybrid perovskites. So it turns out that it's actually relatively simple because it's either linear or parabolic dependence, and that would be a part of our notebook. It of course is possible to run it as the part of the theory modeling. So if you explore the parametric spaces, in fact, I expect that in these cases we can see the most benefit because physicists usually have a pretty good idea about what are the hypotheses operating in the parameter space. The question becomes kind of going back a little bit about the philosophy is what type of problems can be done and cannot be done with the hypothesis learning. So going in general, Bayesian methods are ideally suited to the scenarios where we have the past theory, we have the theoretical models, and we have the high performance computing of some sort. So then given the theory and given the data, we can narrow down the range of the possible theoretical capabilities. So in other words, before the experiment, we have the priors. So this is our prior knowledge. It can be somewhat uncertain. We run the experiment. We generally compress our uncertainty so we know more about the system. So the part, this is something that machine learning in probabilistic programming is exceptionally good at. And this is part of the research that machine learning can do remarkably well. There is a part of machine learning that we don't know how to do well, which is how do we form the new hypothesis. So in other words, that if this is something that we already know, how do we make guesses about what can be out there? So this is complicated because there is a big, I mean, we all know that there is a difference between the serendipitous discovery and the wrong experiment, right? So the experiment can show something new, but for that we need to trust the experiment. So that's the reason why we actually don't publish negative results, because positive results speak for itself, whereas the negative result is believable only if we are absolutely certain about the experimental protocols. So for hypothesis and theory, situation is opposite. So there are a lot of things we can speculate about the unknown, but very few of these things make sense. So forming the hypothesis as the limited number of opportunities that the unknown can take actually takes a lot of time and effort, and it's not clear how it can be done automatically. We can speculate that the hypothesis can be generated randomly, and then we just narrow down the list of random opportunities to those that are consistent with the basic physical laws that we know. That's probably not a terribly good idea. So for the time being, let's assume that this is something that has to be done by humans. And one of the things that we are going to look in the next few lectures is actually how we can steer the autonomous experiments. And one way of doing it is through the hypothesis injection at the different stages of the automated experiment. But we'll get to this point, and for the time being, let's switch to the collab and see how the hypothesis learning operates in the real-world environment. So as before, the collabs are all on the GitHub. And in this case, I'm not going to run through them because that actually takes slightly longer than it is comfortable. So I'm just going to go through the code and illustrate the primary elements of what have been doing and how do we interpret the results. So, I mean, I couldn't resist the temptation to add a little bit of the philosophical introduction to the why we need hypothesis. So our experimental budgets are limited. We cannot run tens of thousands of the experiment to learn physics by random action. We need to choose what experiments we are going to run. And that's what hypothesis allows us to do. How do we implement it? So we start, of course, with the installation of the GPax and the necessary packages. So in this case, GPax, JAX, and NumPy are sort of same as before. We define several helper functions. So these are used to essentially get the data, plot the result, plot the acquisition function, plot the final result. So they're very simple. It's just a representation of the data of the aesthetically appealing form. And after that, we generate some amount of data. So in this case, in fact, in this case, we create exactly the same type of function as we did before. So we have the function which is power law on both sides. So on the left of the discontinuity, we have x power beta. On the right side, we have x power beta 2. We define the values of our parameters. So the location of the jump, the power beta 1 is 4, power beta 2 is 2.5. So same example of the function as we did in the second lecture. And we, of course, define the measurement as the true function plus some noise. So notice that in this case, we actually provided a fairly large number of points in order to sample that. Now, let's define our hypothesis. So we know that our ground truth is the power function. So x power alpha beta 1, x power beta 2. So let's choose three functions that can be possible hypotheses. So one is has two parts. To the left of the discontinuity is x power beta, but on the right it is the linear function, so c times x, and of course there is a jump between them. So our second hypothesis is that we have the function which is linear on the left with the slope b and kind of no offset, and it is linear on the right, so linear and linear. Our third one is exactly the right one. So the third one is x power beta 1 on the left, x power beta 2 on the right. So these are our three hypotheses. Of course, if we deal with the Gaussian processing-based methods, we also need to define the priors. So priors and the hypotheses are as important as in Bayesian inference or Gaussian processes. So prior is our total physical knowledge about the system. So in this case, we choose the priors in a fairly general fashion. So we choose the uniform distribution for the position of the jump. So it is between 0.5 and 2. We choose the beta b having the normal distribution, so with the mean of 3 and width of 1. And we choose the same one for c. And then we define the priors for other two functions. So we have the similar priors for piecewise 2, and we have the similar priors for the piecewise 3. So the very interesting thing to experiment with, so as I mentioned before, the only way to learn this method is actually to experiment with these notebooks at the different settings, starting with the playing with the values of the priors, continuing with the introducing the new functions, playing with the data generation, playing with the noise, until you start to develop some logic for that. And then, of course, applying it for your own problems. But again, I cannot stress how important is the definition of the prior functions, because ultimately, so prior distributions for the parameters, because ultimately that defines your knowledge of the system. And for some distributions like normal or half normal, you can, these priors are relatively weak, meaning that you can shift way outside of your initial expectation for the parameter value because distribution allows it. If you start to choose the distributions like uniform, that can impose a fairly rigid constraint on the values of the parameters. So in this case, you have to be careful. And one thing that you can experiment with is to choose this distribution to be such that it incorporates the ground truth. So our jump is at 1.75. So here it is clearly inside our priors, but you can experiment with what will happen if we choose this value to be from 0.5 to 1. So as before, we also need to specify the priors over the Gaussian process kernel. So if you use the GPax or any other environment, there would be a default versions for the kernel parameters, including length, scale, and the noise prior. Again, it is exceptionally good idea to define them explicitly because these parameters really matter big time and they affect the way how the algorithm is going to converge. So now goes the interesting part. So how do we create the hypothesis learning loop? So hypothesis learning is implemented as basically providing the reward to the model that allows to minimize the predictive uncertainty most. And what you see here is basically the whole set of the definition that allows us to run it. So get best model is straightforward. So for each model, we store the rewards that it got through the process, and therefore we choose the best one. The update record, this is basically we give the model the reward +1 if it minimizes the uncertainty best, and we kind of don't give it a reward if it didn't. So this is how we read out the reward, and this is our step in the hypothesis learning process. So basically, we define the acquisition function. We tell it how much information we want to provide the algorithm. We need to provide some information to work under the hood to make the Monte Carlo chain work better. And this is our Gaussian processing part. So as you have seen already several times before, we define our Gaussian process model using the kernel priors, the model priors for the function and prior for the noise. We feed the model, and then we determine what was the uncertainty. So, and then of course we need to keep track of our experimental points, meaning we perform the measurements on the new points, and once the measurement is performed, we remove the measured points from the list of points where the measurements are possible, so that we don't keep sampling one point over and over again. And this is how the whole thing works. So we generate our seed points somehow. We define our loop. So we define the number of the exploration steps. We define the epsilon. So epsilon is the epsilon greedy case, meaning that if we have models, then 60% of the time we will choose the best model in order to run the experiment. And 40% of the time, we are going to choose a random model. And the reason why we are going to do that, so why the epsilon greedy policies are used, and of course more complex exploitation policies, is because from time to time you want to try something unknown. So it is well-known principle that if we run any kind of automated experiment in the purely greedy form, that means that there is a very high chance of converging to the local minimum. So if our optimal function have multiple minima, and we start close to the relatively shallow one, we will just go directly to the bottom of this minimum and we'll be stuck there. So if we want to explore what happens in the parameter space in general, this is what we use the epsilon greedy approach for. So it simply makes a provision for trying something new and unusual from time to time. Again, it is very similar to how some research groups are doing their research. So if you remember, for example, the famous experiments by Gaiman Novoselov that led to eventually to the Nobel Prize for Graphite, these were the type of experiments that they called the Friday afternoon experiments, where you dedicate essentially half a day a week for doing something that's not a part of your primary research program. And sort of many places have similar traditions. For example, Google allows or parts of Google that I know of allows some of their staff members to spend some amount of time pursuing the curiosity-driven research. So in this case, when we run the machine learning algorithm, it is exactly the same principle. So we need to allow the algorithm to explore the parts of the hypothesis space which are not necessarily clear that they're interesting or not. So there are other ways to introduce the exploration balance between exploration and exploitation. We can talk about them in detail if you are curious, but if we have a finite and fairly short list of opportunities, we just do it through the epsilon gradient. So then kind of all we have to do is to define our list of models, model priors, create the arrays that store our record of rewards, choices of models, and histories. Then we run the warm-up experiment, meaning that we run all models 3 times. And then we run the exploration experiment when we start to choose the model that we expect to minimize the uncertainties fastest. And let's look. So in this case, I have chosen the values of the parameters in such a way that the results are kind of illustrative. But again, feel free to experiment with that. So let's see what happens during the warm-up step. So during the first step of the warm-up, we took our experimental data and we tried to fit it by all three models. And each 3 model give us the values of the parameters, so including the means and including the standard deviations, medians, and it also gives us a little bit of the idea about whether they fit well or not. So remember one thing, that our data on the ground truth is the 2 power laws, x power b to 1, x power b to 2. The algorithm doesn't know that. So algorithm has access only to the data points. Our models, one of them is linear and power law, second is 2 linear, and the third is the power law. So the model number 3 is the correct model. Notice that even in the beginning, we already start to have an inkling that the model number 3 gives us a slightly better result. So here the R hats are exactly 1.0. However, all 3 models are actually plausible. So if we put all 3 of them in the WIAC, it will tell us that it's okay. So we wouldn't be able to separate them clearly. And for all 3 models, we have our usual suspects. So we have the values of the power and slope for the first one. We have the values of the kernel parameters, length and scale. We have the expected noise. We have the position of the switch point. So for the second model, we have the B values, and then the part that pertains to the Gaussian process. And for the third model, we actually have the beta values, kernel parameters, and position of the jump point. Notice that the position of the jump point is actually very far off now. It's 1.17. It should be 1.75. So anyway, then we run the second warm-up step. Again, we evaluate all the 3 models with the addition of the new point that we test. So our parameters are updated. Then we do it 3rd time. So after we are done with the evaluating of all 3 models and choosing our new experimental point, we start to run the exploration using the hypothesis learning. And in this case, this is our step 4. So the algorithm have chosen model number 1. So for whatever reason, the algorithm decided that we need to explore the first model. So see what happens. So these are our measured points: 1, 2, 3, 4, 5, 6, 7. The red line is the reconstruction. The pink region is our uncertainty, And this is our acquisition function. So you can see that for the model number 1, it has jump. Our next measurement point is selected to be here, meaning it wants to find out the position of the jump in the best way possible. But at the same time, notice that the acquisition function, which in this case is expected the uncertainty, sort of suggests that we have a high uncertainty here, high uncertainty here, and high uncertainty here. Anyway, so we run this exploration, we choose the next experimental point, and then the algorithm says that the next point I want to explore is going to be the model number 3. So with the model number 3, our acquisition function looks totally different. So in this case, we still have the uncertainty in these regions, but notice a difference. So in this case, the uncertainty looks like this kind of sausages. So you see that the uncertainty is relatively small, close to the measured points. So at the measured point location, the uncertainty is determined pretty much by the noise posterior in the system. But away from the measurement points, it becomes considerably larger. If we choose the right model, it turns out that the uncertainty distribution becomes very different. So in this case, you can see that uncertainty is almost the same pretty much everywhere. So it's actually a telltale sign that the model is actually correct. We have not parameterized this approach. So for the time being, we use the hypothesis learning only to use the total uncertainty of the predictive model. But this is one of the things that you will notice if you play with the code. So then after we run it, we will see that this is our acquisition function. The algorithm is most uncertain about this point, so it's going to take the next measurement here. So then it runs the exploration, and then it chooses model number 2. So we don't know, we didn't record it, so maybe it has chosen because it was the epsilon greedy approach, so it is a random selection, maybe for any other region. But you can see that the model number 2 actually really doesn't work that well. So you can see that there are two characteristic things going. So remember that model number 2 is a 2 linear segments. So you can see that there are two characteristic aspects of how we can identify that this is not the right model. First of all, our uncertainty becomes considerably larger. So notice that here our acquisition function adopts the value 0.3. So it's pretty small. Here the acquisition function is 3.5. So acquisition function in our case is the uncertainty. So once we chosen the model number 2, our uncertainty in the prediction become much larger. And you can see here from the experimental points and the position of the red curve that they really don't match each other particularly well. And you can conclude it based on the fact that you have these dips here. So that tells you that the kernel length has become very small. And you can conclude it based on a fairly large uncertainty. So this is clearly not the right model, and we can just see it in how the Gaussian process deals with the data. So lo and behold, on the next step, the algorithm decides that this is a bad model. Let's go for the next one. We go to the model number 3. And model number 3 start to look very peachy. In this case, you can see that, again, our uncertainty becomes more or less uniform. Our points are selected, our experimental points fall on the posterior mean reasonably well. Our acquisition function is small, and more importantly, it suggests that maybe we should spend some experimental time in order to determine the position of the jump slightly better. So again, what we've done here is that we follow the breadcrumb of the minimizing uncertainty in order to choose the right model, but from time to time, we let the incorrect, we also try the model that is incorrect. The reason why we are doing it is because we know that this model is incorrect, but the algorithm doesn't. And it's important to check whether it is the case or not. Then if we continue doing it, then we are going through the process several times. So the algorithm start to focus on the model number 3 because it's the right model. But from time to time, it checks the models, again, going back to the model number 2. And again, you can see the same telltale characteristics of the model being incorrect, meaning that there are changes in the predictive uncertainty, and overall the uncertainty becomes larger. So here it is 0.20 at most. Here it is 0.7. So that's clearly not good. And then if we continue the process, you can see that, okay, we went to the model number 1, we went to the model number 3 again, and now the algorithm decided to check what happens on this side of the measurement parameter space. And throughout all this process, we have the evolution of the model parameters. So we update the model that we chosen to try. And you can see how the process goes on over and over again. So in this case, the model number 2 clearly is not the right model. So the algorithm decided that it doesn't fit the data particularly well. So if we continue this process for 15 steps, so 3 warm-up, 12 of the experiment, we get the final result. So this is our median uncertainty as the function of the exploration step. And this is the number of the model. So this is, we started with the model number 2. We do 2 measurements with the model number 3. Notice that in the beginning, the uncertainty actually goes up. So it's important to be persistent. Then we check the model number 1. So this is our initial step. Now we start to have the convergence to something reasonable. So the model number 3 is clearly the leader. However, we gave the model number 2 and model number 1 few opportunities to be checked. That's why we have the epsilon greedy process. In the end, we came to conclusion that model number 1 is correct. We can look at the rewards associated with each model, and we can create the prediction by each model in the end. So this is the prediction by the first model. So it's clearly not particularly good, but it's not that far off. It managed to find the position of the jump, but clearly the behavior on the left and on the right of the jump is completely off, as it should be. So model number 2 clearly did not produce a very good answer. So the kernel lengths become very small. So you sort of start to treat every noise peak as the real element of the data. So, and compared to that, model number 3 produced the beautiful answer. So our measurements are fairly noisy, but in the end, we get the behavior which is almost ideal. Our uncertainties are uniformly distributed across the whole interval. So the whole hypothesis learning actually worked. And sort of that's how it works for the one-dimensional systems. So before we go to the 2D cases, do you have any questions that I can answer?
I do have one question. So like the here like we offer like the 3 like the models, then we know like one of them is correct. Like if we in the end we find like all the error like pretty large, does that conclude in like the it's probably described by something else or some like hidden parameters or something like that?
So you're right that we did the experiment where one of the models is correct, and we kind of expected to converge. If all 3 models are incorrect, then things depend on whether our measurements come with what is the level of the noise in our measurements compared to the difference between the models. If our noise is sufficiently large, we can find the model that still fits the data remarkably well. If And obviously, when I talk about the noise, it is important to take into account both the noise prior and the noise in the data generation process. So the true noise versus our expectation of the noise. So the same logic as we had in the first lecture will apply in this case. If we expect the noise to be large, but the real noise is small, then the model will simply not pay attention to the small deviations of the, then the algorithm will not pay attention to the small deviation of the prediction from the data. If we absolutely trust the data, but at the same time, our noise generation process is fairly high, so we are certain that the measurements are precise, but in reality they are not, then the algorithm will start to interpret every noise peak as real. With time, it will converge to the right answer because it will learn how to average over measurements in the adjacent locations. But then we are not talking about the experiment run in 10 or 20 steps. So then we will have a considerably longer amount of measurements required for the noise prior to converge to the true value. Practically, when we apply this algorithm for the real world scenarios, the thing that matters is how many steps we have, how far off we are, and that's basically it. If none of our models is correct, then all of sometimes one of them will win, but it's possible to see that the structure of the uncertainties become non-uniform. So in some sense, it becomes the Bayesian equivalence of the analysis of the residues and the classical least square fits.
I see. The other question is like, like the, so like for this example, it takes like, over 10 steps to select which model is better. So like, will the difference between different assumptions, I mean, for example, if one assumption is very similar to the other one, will this take like longer to give you the final result?
I mean, not all models are distinguishable given the experimental budget, right?
That's
So
true. Yeah.
the difference between the models is relatively small. Our experimental budget is limited, and the noise level is sufficiently high. Then the models would be inseparable. That's actually the reason why I'm saying that the priors that we put on the noise and the model parameters are actually exceptionally important, because we don't do it in synthesis, and we don't do it in microscopy. But if you work in the fields like high energy physics or cosmology, they put a really large importance on the choice of priors if they do analysis in the Bayesian way, because in those cases, everything is determined by how the priors are chosen. So in the less quantitative areas of the physical sciences, we typically use the criteria which are less principled. So we say that, hey, this data is fit by this model better, this data is fit by this model better. But realistically, we don't have the, we cannot quantify our degree of certainty particularly well. So Bayesian analysis, either if we use the Bayesian inference on the data once it's already obtained, or if we use the structured Gaussian processes or SGP for active learning, allows us to make this type of analysis in the principled manner. But it becomes principled if and only if we specify the priors and we say where the priors have come from. So, for example, one thing you can experiment with the notebook is imagine that you have three models, and this model have the same functional form, but they differ in priors that you put on the position of the jump. In one case, the jump can be from 0.5 to 1. In another case, it would be from 1.5 to 2. So these are two hypotheses. And then you can figure out how you will see how the hypothesis learning algorithm allows you to choose the right hypothesis among several.
Got it. Yeah, thanks.
And again, kind of on the most general level, once we go to the things, so simple Gaussian processing can be applied to everything. In fact, if you want to apply it for tuning of the microscope in the relatively kind of what knobs you want to tune to make it work better, it will work. If you want to use it for material selection, it also will work. So that's the beauty of it, that it's a relatively reliable out-of-the-box algorithm which tends to converge with time. Once you move from the Gaussian processes to the SGP and hypothesis learning, it actually puts the emphasis from the data scientists that you work with to back on you as a physicist to come up with the right models and the right priors for those models in order to start the experiment. Because if you don't, then it's better not to have any expectations, meaning start with the simple GP, than to choose the wrong model and kind of try to push it through one way or another. So this being said, let me show you how the Gaussian processing works beyond the one-dimensional case. So again, GPax has been developed with experiment in mind. So with the experiment in mind, it can work for relatively low dimensional cases, so for 2, 3, 4 dimensions. It is not designed to work with more than 4 dimensions for the time being. If we need to deal with the higher dimensional data, we are going to use the deep kernel learning, which basically creates the dynamic embedding for the high dimensional vector in order to represent it in the and then GP essentially works on the latent space of this high dimensional embedding. The second thing for the GP is that it is not for the GPax, sorry, is that it is developed for experimentalists, meaning that it's defined to work as simple as possible, but it will not scale for the supercomputer, at least in the present form, primarily because we sort of typically don't have a direct access to the supercomputer when we run the experiment on the microscope or material synthesis. And most of the time, we actually don't need it. In fact, in all the cases that I'm aware of, for the time being, we actually didn't need it. Things can become more complicated with time, but for the time being, that's where we are. So the important thing, however, is that we don't need more than 4 dimensions, but we definitely need more than 1. So what this notebook illustrates is essentially the whole all the components of the Gaussian process, for including the regular Gaussian process and structural GP and hypothesis learning for 2-dimensional data sets. So kind of let's I will have to leave slightly early today because of some baby appointment. So let's just go in the next half an hour. Let's just go through the structure of this notebook and see what is the difference between this notebook and the previous 4 notebooks that we use as an illustration. So again, the installation part is exactly the same. The imports are exactly the same. Now the question becomes, how do we generate the data? So in this case, this notebook was developed specifically for the automated discovery of the hybrid perovskites. So basically our parameter space in this case is 2-dimensional. So this is just something like a x b1 minus x lead, and then you have second component. And we have a band gap dependence of the composition of the components. So there are there are several models that we can use for it as the ground truth. So one of them is linear in one component. And so we introduce some help functions, so which have a linear part and the parabolic part. We introduce for each material, we introduce basically the ground truth behavior of how the band gap depends on the concentration of the components. And as usual, we add noise to that. And it's easier to represent it as the graphs. So for one composition, it is linear function, linear in one, linear in the other one. For second, it is parabolic for one component, but the linear in another component. For third, it is vice versa. It is linear in this one and parabolic in this one. And the fourth model is parabolic and parabolic. So these are 4 ground truth models. So then we have to go through the same process and define our ground truth functions. So we define our ground truth parameter. So this is our chosen model and added noise. And we define our mean functions, and we define a trial function. So the trial function is something that we are going to use to fit our data in this case. So as usual, we define the single Gaussian process step. Notice that in this case, the algorithm is exactly the same as in the first case. So the only difference is that once we use the GPax exact GP function, which actually defines the Gaussian process model, the only difference is that our input dimension is 2 rather than 1. That's it. Everything else is choice of the kernel, kernel priors, mean functions, and so on would be absolutely the same. Then we do the fit, and then we kind of can have fun. So then we, let's say that this is how we define our training data for the time being. So let's assume that this is your 2-dimensional phase diagram. These are the locations where we took the measurements. So this is where the measurement point, and obviously the color is the value of the measured function. So this is how the regular Gaussian processing is going to run in this case. So we choose the 3 steps. We use exactly the same approach as before. Our acquisition function is the uncertainty. So once you have y sampled, this is the samples of the posterior functions. Once we squeeze them and measure the variance, this is the dispersion. So once we run the automated experiment, you can see how we explore the evolution of the posterior mean and the uncertainty. So this is our automated experiment in the 2-dimensional parameter space. One thing that you will notice, which is kind of fun, if you think about it, is that if we run the automated experiments in this type of settings, in the beginning, we are always going to start explore the points in the corners, because in the corner of the parameter space, the uncertainty is actually always maximal. So you see that the first measurement point, first our uncertainty is maximum here. So we took the first measurement here, uncertainty went down. So then the uncertainty is highest here. So we took the second measurement point here. And then once we've done it, we can basically calculate our posterior mean, compare it to ground truth, and take the difference. So the measurements were noisy. However, you see that we actually hit the right value reasonably well. Now, how do we instantiate the structured GP? Same principle. So except that now our GP step now explicitly includes the mean function and mean function prior. And you run the process exactly the same way. Notice that in this case, our posterior mean was a kind of Gaussian, which is not exactly the right function. Nonetheless, the process runs, and again, we get the posterior mean and the uncertainty, and the process sort of navigates. So if we try to visualize the behavior, in this case, the answer doesn't look so good anymore. Why? Because our mean function was actually incorrect. And then the final thing that we can do here is the hypothesis learning. And in this case, we kind of decided we did it with the kind of went the wrong road by defining all 4 possible models as the probabilistic models. We define the priors. So it actually takes quite some time to go through this and make sure that there are no problems in the code and all the parameters are taken care of. We define our utility function for the hypothesis learning as before. And then we start exactly the same hypothesis learning process. So notice that the structure of the code is absolutely the same as for the 1-dimensional case. We define the number of exploration steps. We define our number of the warm-up steps. We define our epsilon, meaning how often we explore the wrong model. And this is how the process navigates. Let's go to the beginning. So in this case, we don't plot the result. We just start with the 3 warm-up steps as before, where we update all models, and you need to keep track of what are the parameters. So this is linear one. This has the quadratic component. This has 2 quadratic components. So we can continue that, and we can keep track of the output of the process. So it sort of will take quite a while. And after we do that, in the end, we can figure out which of the 4 models is actually the correct one. And you can see that once the process has been iterating, we have identified that one model has been the right one. So the important thing here is that for these values of parameters, we actually had to run the experiment maybe 30 times, which is, if we want to explore the 2-dimensional phase diagram, is actually not too bad, to be honest. So that's actually within the scale of something that can be done manually if you synthesize the films by hand. Of course, for high-dimensional space, the problem becomes there are more technical problems, so we need to define the high dimensionality functions, we need to check them and so on. But basically, again, the efficiency of the structured hypothesis learning would be much higher than the efficiency of the regular one. So again, you're welcome to play with this notebook as well. Realistically, one-dimensional notebooks are best to learn. So practically, for 2-dimensional notebooks, it's actually more considerable effort to convince them to operate. So it's probably worth doing if you already have the specific problem that requires 2 or higher dimensional models. So, but this notebook can be used as the starting point. So this being said, again, if you have questions, let's talk more about it. If not, then at the next lecture, we are going to talk about the manifold learning, variational out encoders and encoders decoders, meaning the techniques that are required to apply Gaussian processing and automated experimentation for scenarios where our parameter space is very high dimensional. For example, process optimization, discovery in the molecular systems, or automated experiment in microscopy. So let me know if you have more questions on the things that we discussed. Okay, so if no, then the most important thing is until this moment is kind of try to go before we go to the next lecture in the coming week, try to go through these notebooks and make sure that you are comfortable with the values of with the definitions and the values of all the basic parameters in the Bayesian optimization, kind of going from basic definition to the interpretation of the process. And most importantly, experiment with these notebooks for the different values of the priors, functions, noise behaviors, and so on and so forth. Because there is no other way to learn these concepts. So once we move from the active learning in the low dimensional parameter space to the high dimensional parameter space, the key trick would be there is to understand how we learn to represent the high dimensional data through the low dimensional embeddings. And at the same time, how do we navigate this low dimensional space towards the target functionalities? So as I said, to the best of my knowledge, there is simply no understandable references, meaning outside of the CS domain, where these concepts are explained. So it's all about experimenting. Sounds good? Okay, so if so, then let's call it a day. And as I mentioned, kind of once you have babies, sometimes babies takes preference. Talk to you.